everyone in this work entitled 3D Printed Paste Design, based on zinc oxide nanoparticles, rheological properties, printability, and photocatalytic efficiency. We present for the first time a novel and simple methodology to achieve 3D printable pastes based on zinc oxide nanoparticles, 61% by weight. Here we find that the addition of small amounts of silicon oxide nanoparticles, 1.25% or 2.5%, in the presence of different volumetric proportions of water. Glycol leads to 3D printable pastes by the technique of direct ink writing, showing an excellent retention of shape, periodicity, and self-supporting behavior. Nanoparticles silicon oxide work like an inorganic binder, and glycol as a plasticizer. Rheological and 3D printing assessments revealed the optimal printability region, wherein the gel point this. The methodology was, we have zinc oxide nanoparticles and silicon oxide nanoparticles. We add water and glycol, we mix, and by direct ink writing, we do the monolith where we subsequently undergo a heat treatment of 400 degrees Celsius for 6 hours. Finally, it is applied for photodegradation of bisphenol A. And results, as shown in Figure 2, the pastes that obtained the desired properties were those that had 2.5% by weight of silicon oxide in all volumetric ratios, 60-40, 55-45, 50-50, 45-55, 40-60, water, glycol, and those of 1.25, with the ratios 55-45 and 50-50. All this is verified with the rheological properties. In the strain versus stress curves, we can observe that those of 5% do not have resistance to deformation, which resulted in hard pastes that dried quickly and could not print their ink. Those of 2.5% have that plasticity, there is elongation. This resulted in fluid pastes, with plasticity and excellent for printing, as well as the curves of 1.25%, but only those of 55-45 and 50-50 that presented the same behavior as those of 2.5%, and those that did not have silicon oxide, that is, 0%, were liquid that by continuing with more capable of the print, they could not retain each other and collapsed. In Figure 3, a printability zone was found where it corresponded to the point of gel versus oscillatory stress of each print. That was the one where the printed with the desired properties are, the transition one, which was the area where the ink could be printed up to certain layers from there, showed a lack of ownership in the ink and the non-printable. In subsection B, we can observe XPS, UV VIS, and scan electron microscopy, where it is proven that the monoliths have the same physicochemical properties. That is, there is no variation with zinc oxide powder, since they have the same band gap and the 2p peaks are shown, just as there is homogeneity in its structure. In Figure 4, we can see that different morphologies can be made with the printable pastes. They also do not present fragility when used. The layers of the monolith have self-support. Lost scaffolds exhibited remarkable photocatalytic activity, high recyclability, 3 times, and easy reactivation for BPA degradation, under 380, 780 nm range of irradiation as in potential application. BPA photodegradations during 350 min were as follows. Cycle 1, 95%, Cycle 2, 80%, Cycle 3, 70%, and reactivation, 80%. In conclusion, it is a good route for 3D printing of ceramic materials free of organic binders that allows a new path for 3D printed photocatalysts, recovering the material and encouraging recycling. Thank you.